Hello, and thank you for tuning in to the Atrium Cardiology Collaborative's latest educational video. My name is Zachary Nolan. I'm an assistant professor at the University of Maryland School of Pharmacy. Today I'll be walking you through a diagram of a left ventricular pressure time curve to help demonstrate the significance of pressure changes in the heart and how it relates to cardiovascular diseases, particularly as it relates to valvular heart disease. The diagram shown here is referred to as a pressure time curve. Now, before you get overwhelmed by all the squiggly lines and numbers, I want to orient you to where we are in terms of the cardiac cycle. At the top of the pressure time curve, you'll notice there is an EKG. This will help orient you to where in the pressure time curve you're looking at and correlate it to the cardiac cycle. For example, we know that the QRS complex is depolarization of the ventricles in that, under normal circumstances, systole occurs after this depolarization and is represented here in turquoise blue. During this time, it makes sense that we will see a rise in ventricular and aortic pressure, as we'll talk about momentarily. Likewise, diastole, which occurs after repolarization of the ventricles, is represented here in green. Now, to orient you to the pressure time curve depicted here, note that on the x-axis we are looking at time, and on the y-axis we are looking at pressure as it relates to various chambers of the heart. I've highlighted the left ventricular pressure, depicted as the bottom solid line, which will eventually turn blue, and the aortic pressure, depicted as the top dotted line, which will turn red. As we start from the far left, note that this diagram begins in diastole, and that during this time, the left ventricular pressure is considerably lower than that of what is seen in the aorta. This low pressure in the left ventricle during diastole allows it to receive blood from the left atrium and increase preload. Ventricular volume increases during this time period, but pressure remains relatively constant until systole begins. At the time systole starts, you'll notice the mitral valve snaps shut as the result of rapid increasing ventricular pressure. This is depicted by the purple circle with the number 1 within it. Following mitral valve closure, for a brief period of time while the aortic valve remains closed too, the ventricular pressure rises and blood is neither leaving nor entering the left ventricle. This period of time is referred to as isovolumic contraction. Now, once the pressure in the left ventricle gets to a point that it surpasses that of the aortic pressure, it forces the aortic valve to open, allowing forward blood flow. Once this point is reached, we see the left ventricular and aortic pressure rise and fall with each other until myocardial contraction is completed. As the forcefulness of the contraction wanes and diastole begins, the left ventricular pressure falls below the pressure in the aorta, which causes the aortic valve to close. Following this, and analogous to what was observed with isovolumic contraction during systole, we see a brief period of isovolumic relaxation during diastole while both aortic and mitral valves are closed. As left atrial pressure rises and left ventricular pressures continue to fall, the mitral valve once again opens and allows passive filling of the left ventricle. This diagram effectively demonstrates the pressure changes that occur during one cardiac cycle. Taking it a step further, we can look at not only the pressure changes as it relates to time, but also the EKG tracing, volume changes, and heart sounds as it relates to time. This is referred to as a Wigger's diagram and is a useful tool to visualize both electrical and mechanical changes in the heart as it relates to time. The purple line in this diagram represents volume, and as you can see, it rises and falls inversely with diastole and systole, respectively. Also shown here is the EKG tracing and heart sounds that can be heard as the valves close. Finally, to show how this relates to the pathophysiology of cardiovascular disease, let's look at the pressure time curve in two examples of valvular heart disease. The first example is a pressure time curve we would see in someone with severe aortic stenosis. The distinguishing feature of the pressure time curve in severe aortic stenosis is the difference in the peak pressures in the left ventricle and the aorta. As you can see by the blue shaded area, and unlike the prior examples I have shown you, the peak left ventricular pressure far exceeds that of the aorta. This is because the calcified stenotic aortic valve in severe AS requires a much higher pressure to move the same amount of blood through the relatively small orifice of the aortic valve. The second example demonstrated here is in a patient with aortic regurgitation, also referred to as aortic insufficiency. The distinguishing feature of this pressure time curve is the rapid fall in aortic pressure that is observed at the beginning of diastole, depicted here and shown by the arrow on the curve. This is due to backflow of blood into the left ventricle during diastole, which promotes a rapid decline in aortic pressures. That concludes this video of left ventricular pressure time curves. I've listed a few other related videos that you can find on our YouTube channel, and I'd like to thank you all for watching. And if you'd like this, please let us know on Twitter and follow us at AtriumRx.